Welcome back for the second part for lesson 8.1. We're introducing hypothesis testing, and we are looking at what distribution we are going to need for the hypothesis testing. So if you're using are testing a single population mean and the standard deviation is unknown, then we are going to use X bar is normally distributed, but we're going to be using the T distribution. Okay, so the T distribution is what we're using with a degrees of freedom of n minus 1. Okay, so the population parameter mean mu is the estimated value for the point estimate for, and we're going to use X bar for that. And then we're going to have a standard error of the standard deviation of the X divided by the square root of n. If you are testing a single population proportion, the distribution for the test is going to be normally distributed, and we're using the Z distribution. Okay, so where the population parameter is P, we're estimating that with P hat, and we calculate P hat using X divided by N, where X is the number of successes and N is the sample size. And then our standard error here is the square root of P times Q divided by N. So example 7, 8, and 9 are asking us to decide what distribution we're using. So 7 says, which distribution do you use when the standard deviation is not known and you're testing one population mean? And we're going to assume our sample size is large. So we're going to be using the T distribution of alpha and degrees of freedom. Example 8 says, you are performing a hypothesis test of a single population mean using a student's T distribution. What must you assume about the distribution of the data? So we know that we're using a T distribution, so we must be assuming that our data is normally distributed. And the sample size is greater than or equal to 30. Example 9 says, you are performing a hypothesis test of a single population proportion. You find out that n times p is less than 10. What must you do to be able to perform a valid hypothesis test? So we would have to increase the sample size. Okay, next up, we are going to run a little experiment. So I would love for you to pause the video if you can and grab a six-sided die, and we're going to read the instructions here. We're going to have each student roll the dice 12 times and tally the number of fives they roll. Have each student share their total number of fives and put those numbers in the table. So, oh, I got a 5 on my first roll. So I've done 2 rolls and the number of fives. I've only got one of them. Oh, I got another one. Oh my gosh, I'm getting so lucky. Nope. Oops. I got another one. Nope. I got another one. Nope. I got another one. Nope. Nope. The 3. Okay. So I'm going to collect data from the class. And so it looks like 2 people got 0 fives. 5 people got 1 5. 7 people got 2 fives. Four people got three fives. No one got four. No one got five. I got six. Woohoo. No one got seven. No one got eight. No one had nine or 10. No one had 11. And it looks like we had somebody that said they got 12. Hmm. What was the outcome? We just entered the outcomes. Doesn't seem reasonable. That is a good question. I mean, you saw me roll my six fives, and that was unusual, I think, here. So that one is already seeming unusual, but this one down here, I'm questioning that person. So hard to believe someone rolled 12 fives in a row, right? Hard to believe someone rolled 12 fives in a row. So it says, how could we decide if it's reasonable or not? So we might be thinking, is this unusual? Do we believe it could happen? Do we think their die was fake? What could be here? So some of the techniques we've been using so far is we said that if our z-score, our absolute value of the z-score, if it's bigger than 2, so outside of the standard deviations by 2, above or below the mean, we said that's unusual. Or we said if we look at probability of our outcome being less than 5%, right, or 0.05, we said that was unusual. So using our discrete probability, what is the probability of getting exactly 12s? So when n is 12, having x is 12, and the probability of getting a 5 on one roll is 1 out of 6. Okay, so if we put that probability into Desmos, we get a very, very, very small number. And then if we want to look at the z-score would be getting 100% of the time, so 1.0, subtracting this 1/6, which is the same as 0.167, or 16.7% of the time, divided by 0.167 times 1 minus 0.167 divided by 12. That comes out to be a z-score of 8.54. So this would be considered extremely unlikely for this to happen. So we want to have a way that we can prove this, that this is an unusual situation here. And so that's what we're going to be doing by formally putting this together with hypothesis testing. And I have to tell you that the person that rolled 12 fives is because I gave them this die that only has fives. So that's what happened there. So let's go ahead and turn the page and talk about rare events. So rare events are, suppose you make an assumption about a property of the population, which we did. We said that we assume that we're going to roll a 5 1 out of 6 times. Then you gather sample data randomly. If the sample has properties that would be very unlikely to occur if the assumption is true, then you would conclude that your assumption about the population is probably incorrect. Remember that your assumption is just an assumption. It is not a fact, and it may or may not be true. But your sample data are real, and the data are showing you a fact that seems to contradict your assumption. Use the sample data to calculate the actual probability of getting the test result, called the p-value. The p-value is the probability that if the null hypothesis is true, the results from another randomly selected sample will be as extreme or more extreme as the results obtained from the given sample. Okay? So that means looking at the rolling of the die that we just did, what is the probability of getting 12 fives or more. And we said that it was very, very likely, almost zero. And that would be about 8.5 standard deviations above the average. So very, very, very unlikely. Okay. So let's look at an example. This is example 10 here. It says, suppose there is a claim that certain population has a mean. I just want to make sure we didn't already have examples. No. Um, suppose that there is a claim that a certain population has a mean mu that is different than 6. You want to test this claim. To do so, you collect a random sample from the population and perform a hypothesis test at alpha at 0.05. So this is what we're looking at, 5%, okay? So remember H0 is the population symbol for both, and we're comparing it to 6. The H0 is always an equal to, and we were testing at a non-equal to. Suppose you also know the following information. The value of the test statistic based on the sample is 1.734, and the p-value is 0.083. Okay. And so we are drawing what this picture would look like. And if you use the p-value method, we are going to compare our p-value to our alpha. Our alpha is 0.05. Our p-value is 0.083, which is greater than. So we do not reject H0 because p-value is greater than alpha. We only reject if our p-value is less than alpha. That's if you're going to use the p-value method, that's always what you're looking for. If your p-value is less than alpha, you reject no matter what. And then our test statistic is 1.734. And this would be a two-tailed test here. So out here is, this is my, out here's my danger zone and my danger zone out here. Okay. But we are right here. We're not in the danger zone. And we're going to find out what our Z of alpha divided by 2 is 0.025. So we're going to find our Z of alpha divided by 2. You can use the table in the back of your course pack that I provided for your alphas. And then I'm going all the way down to the bottom here. Alpha at 0.025 is 1.96. And so my 1.96 would be my danger zone, or negative 1.96. And I'm not in the danger zone because I'm only at 1.734. So we do not reject. So you're either going to use a critical value here, critical Z, or you're going to use the p-value method. Remember, the p-value method you only reject if you're less than alpha. Your p-value is less than alpha. So based on your answer to part A, whoopsie, which statement below is true? Since the p-value is less than or equal to the level of significance, the null hypothesis rejected. Since the p-value is less than the level of significance, it's not, it's greater than, so it's one of these. Since the p-value is greater than the level of significance, the null hypothesis is rejected. Or since the p-value is greater than the level of significance, the null hypothesis is not rejected. This one right here. We're kind of putting it all together, how to write the hypothesis statement, how to find your test statistic. We're going to work on that in a little bit, but we were talking about how to reject and then how to interpret that rejection. Let's look at example 11. It says a normal distribution has a standard deviation of 1. We want to verify a claim that the mean is greater than 12. A sample of 36 is taken with a sample mean of 12.5 and standard deviation of 1.7. So we have state the hypothesis. So the hypothesis is mu because we're talking about mean and it's always equal to, and it's a claim against 12. And they're claiming it's greater than 12. So HA is mu is greater than 12. Calculate the test statistic. So the test statistic is going to be a t-test statistic, and it's going to be the sample mean 12.5, subtracting what we think is true about the population 12, and then the sample standard deviation of 1.7 divided by the square root of n. They said 36. Calculate the p-value. So we're going to go ahead and calculate this right here. So we have 12.5 minus 12. So this is 0.5. This is 0.283. It comes out to be 1.767 or 1.7668. It depends on how many you round to. Calculate the p-value. So we are looking to see what the probability that this would be greater than that. The probability that this t would be greater than because it's a greater than. So everything's going to be over here because if it's a two-tailed, then we're going to have drawn on both sides with that equal on both sides, but we don't. We have it right here. And they did not give us an alpha to go by, so we're going to use alpha 0.05 always. And then our degrees of freedom is equal to n minus 1. So that is 36 minus 1 is 35. So using the back of the book, formulas. $35 is right here, and 0.05 is right here. So it's 1.69. 1.69. So the danger zone is 1.69. And we're going to calculate a p-value, but I want to show you that our test statistic is in the danger zone. So we are in the danger zone. And in Desmos, um, we can find the probability of this being further is going to be and will be being further away than 1.767 standard deviations is 0.04. And we're going to get more into this calculation later, so I'm not going to go to that right now. But it is less than alpha. So because we're in the danger zone, we're going to reject H0. And also because our p-value is 0.04, the likelihood of this happening is less than our alpha, which is 0.05. We reject H0. Okay. So this is significant. So statistical significance. When observed results from a random sample are very unlikely, in this case, that is true, due to chance if the null hypothesis were true, so we reject the null hypothesis. So we use here, the classical approach is looking at the standard deviations. We had a critical t-value. Compared to our test statistic. That's the classical approach. And the p-value approach is looking at the probability that you would be this many standard deviations away or further. And that came out to be 0.04, and that is less than alpha. So those are the two ways that you can prove something is unlikely. So let's see. It says, if the p-value is less than alpha, then we reject H0. If not, if we are not given an alpha level of significance, then use alpha equals 0.05. Or if the test statistic is outside the critical value. So here are the two test statistics. This is for quantitative data for means. We're using the t distribution. And for proportions, we're using the z normal distribution. Okay. So when I talk about the danger zone, I'm talking about out here, wherever that critical value is. And in here is do not reject. So once we decide if we're rejecting or not rejecting, then we have to explain our decision. And so step 5 is deciding whether you're going to reject. So if you reject the null hypothesis in step 5, then in step 6, you're going to explain it like this. There is sufficient evidence to support the claim that whatever H1 said, okay, your alternative hypothesis. If you do not reject the null hypothesis, so you do not reject H0, then you're going to say specifically there is not sufficient evidence to support the claim that whatever H1 or the alternative says, okay? So you have to be careful for that. So let's look at our last example. And this is example 12. For each situation, decide whether the null hypothesis should be rejected. So we said if alpha is less than, if the p-value is less than alpha. So p-value and alpha. So in this case, alpha is 0.01, 0.042. It is greater than. So we do not reject H0. Then on this one, we have 0.086 compared to 0.10. So it is less than, so we do reject H0. Then we have p-value 0.035 compared to 0.05, and it is less than, so we do reject here as well. And then our p-value is 0.017 compared to 0.01, and it's slightly bigger, slightly, so we do not reject H0. And that is all for lesson 8.1. We got a lot in lesson 8.1 that we have to put together here. So we're going to actually complete our very first hypothesis test in the next video. Reach out if you have any questions.